Flow work is a weird thing. Now, the nice part is you can use the conservation of energy equation that's given in your lecture notes without actually understanding the origin of flow work, but it's weird because all of a sudden there's this work that's being done even if you're just passing fluid through a rigid pipe that kind of flies in the face of everything we learned about work up until this point. Let me go into the origins briefly just so you can sleep well at night knowing that the flow work has been taken care of. So let's imagine that we're given a pipe with some sort of fluid. I drew it to look like water going through an inlet and then out an exit with some velocity v. Let's focus on the exit specifically, and particularly the pressure at that exit. So what is that pressure doing? Well, it's a pressure and the exit has an area, so if you recall, pressure times an area is a force, and you can imagine that that force is being exerted to the left, namely into the system itself. That sort of stuff happens with fluids all the time and you never really have to notice it. But there's also a force being exerted to the right, and the problem with that is that this force, I've drawn as an arrow to the right, is acting on the environment because I've shown you the system boundary at the exit, so the force at the exit must necessarily be applied to the environment. Now, I'm going to focus on the exit here. There's going to be another similar force at the inlet pushing into our system from the environment. The logic and much of the math is exactly the same. If you understand flow work at the exit, you can understand it at the inlet. Okay, so let's put in our environment there. So this little disk of environment right up against our system is what's feeling that force, and that's the origin of flow work. So let's define this to be the positive x direction. We'll need that in a minute. And let's just start from our comfortable definition of work, namely that work is the integral of p dv. So everybody's happy with that. We've had to use that a bunch of times. Let's assume that the pressure is constant so that if we're integrating a PdV equation, we can pull pressure out of that integral. Now you may say, well, wait a second, I don't really get what volume is changing here. What you can imagine is that the pressure that is at the edge of the system would actually want to push on the environment and exert a volume change. Now, we're going to be able to write that volume change in terms of the motion of the fluid, which will be nice because we actually understand that better than sort of an abstract volume change. Let me show you what I mean. First, given that we're doing energy conservation with an open system, let's change to W dot. So we'll take the time derivative of both sides, and doing this sort of discretely, assuming that, again, we're just interested in some change in volume, then P delta V over delta T must be W dot. Okay. So what happens for a constant area? So for a pipe like this, where the sides are parallel to one another, it is constant area everywhere cross-sectionally. So for constant area, we can assume that actually this change in volume is going to be that cross-sectional area times some change in x. That's why I had to define the x direction. So we can substitute that in for delta v. That means that W dot equals P A delta x over delta t. We'll keep that. All right. So if we're working with that, well, let's rewrite it in sort of a suggestive way. W dot equals P times A times delta x over delta t. Well, everybody knows what that last fraction is. That's just the velocity. So it's the velocity of the flow. If you're moving in the x direction, then you're moving along with the flow at delta x over delta t velocity. So we can substitute in the velocity v, namely the one that has ears, in for delta x over delta t. Now we can appeal to the definition of m dot. So if you remember, the mass flow rate, m dot, is rho times a times the velocity. So we can rewrite this in terms of the specific volume if we want to. I generally try to avoid that because of all the v's, but in this particular instance it'll be nice. So m dot equals a times the velocity over the specific volume. And one more step, that means that m dot times little v equals a times the velocity. Okay? Well, the whole reason to do that was that this expression right here, so a times the velocity, is the same as this part of the expression up there for W dot, so that means that we can substitute in m dot v into the expression for W dot. So let's do that. W dot equals the pressure times m dot v, and lo and behold, that is the expression that was mentioned in your lecture notes as being the form of the flow work power, namely W dot. So W dot equals m dot pv. Part of the argument has been completed, so I hope I've convinced you that at least that form makes sense. Certainly the units make sense. What about the sign, though? Because that's a little weird. Well, actually, it retains the same sign that the overall conservation of energy equation has. Remember, change in total energy is Q minus W. So for that case, if W is positive, that must mean that the system is doing work on its environment, which is clearly the scenario that I've outlined up there in the figure. That flow would be doing work on its environment. It's pushing out into the environment. So in that case, we would expect, for this result, W dot greater than 0 means that that power is exerted on the environment, and that corresponds to the case of exit flow. For inlet flow, you have the opposite case, namely that W dot less than 0 is done on the system. Now, it's still the case that those M dot PV terms will retain the sign of W overall, so that's how they end up getting the signs that they get in the conservation of energy expression. But now that we've accounted for the flow work, you can put in the PV part of that into an enthalpy and then never actually have to worry about it again. So it's something you need to understand, but generally speaking, you can use the conservation of energy expressions without having to think about this happening every single time. From here on out, if you see W dot subscripted CV, that means that we're talking about the more traditional forms of work, like maybe the pipe is compressing or expanding, or maybe there's some sort of turbine involved that's going to end up taking out energy from our system and doing work on the environment.